Hello everyone, this is Yiling Nan from Department of Civil and Environmental Engineering, University of Alberta, Canada. It is my great honor today to share one of my published works in AICHE Annual Meeting, which is sleep length of methane flow under shale reservoir conditions, effect of pore size and pressure. Classified as source of natural gas, the shale gas has emerged as an important energy support. Based on International Energy Outlook prediction, the ratio of shale gas in the total natural gas production increases year by year as shown in the figure. I would like to introduce more about the shale gas and the shale reservoirs, about their characteristics. So the shale gas is a natural gas that is found within shale formation and usually contains 95 mole fraction of methane. The shale is fine-grained sedimentary rock characterized by small pores in nanometer scales. And here we show a shale gas outcrop to make a more intuitive understanding on shale rocks. As we emphasized here, one of the characteristics of shale reservoir is that the pores are in the nanometer scales. And these characteristics make them be different from the conventional gas reservoirs by having extremely low permeability. The permeability of shale rocks is in this order, and this value is several orders lower than that from the conventional reservoirs. Good thing is that thanks to the recent progress in the techniques of horizontal drilling and hydraulic fracturing, which creates more fracture networks, thereby increase the permeability, the shale gas recovery is more than just talking in theory nowadays. The shale gas production process encounters wide-scaled gas flow. Let's imagine we have shale reservoirs in the dark green region. In order to recover the shale gas, we first drill a horizontal well and make more fractures using the hydraulic fracturing, so we get the formation conditions like this. If we zoom in and to see the fracture part, two different scaled flow can be observed. One is the flow of gas in the hydraulic fracture, which is in macro scale. The other one is the gas flow from nanopore to fracture, which is in micro scale. And if we further zoom in to see the shale formation, which is not affected by the hydraulic fracturing, the flow is in the nanoscale. So considering the flow in the nanoscale is the speed control step, understanding the gas diffusion and flow in shale nanopore is very important for shale gas production. Another reason to exclusively study the nanoscaled flow is that the nanoscale fluid transport is different from those in bulk. As we can see from this table, the flux of the fluid in the nanotube is around thousands higher when compared to the no-slip hydrodynamic flow. For better understanding, I would like to introduce a little more about the no-slip boundary and one important parameter in this work, which is slip length. In conventional hydrodynamic equations technique, Navier-Stokes equation, for example, we assume the velocity of the fluid at Pore is zero, although there are no theoretical foundation for this assumption. This is because although slippage may be present at macroscopic scale, it usually have negligible effect of flow characteristics. At the nanoscale, however, the flow slip can have a significant effect on the flow rate. Here is the schematic diagram of velocity profile with surface slippage. In order to quantify such a slippage, scientists use the slip length, which is the distance at which the linearly extrapolated velocity reaches to zero. Undoubtedly, determining the slip length can better assess the flow behavior in nanopores. Let's come back to our previous discussion. We was talking about that the understanding the gas diffusion and flow in shale nanopore is important for shale gas production. And knowing the fact that determining the slip length can better assess the flow behavior in nanopores, we came to the conclusion that studying the slip length of shale gas in the shale nanopores is important in shale gas production. With this in my mind, I did some literature reviews on the sleep length studies in relation to the shale gas production. I first studied the typical reservoir conditions and summarized them in the following diagram. The x-axis is the temperature and the y-axis is the pressure. I found that the conditions for the shale gas reservoirs are rather in the high temperature and pressure conditions. However, to our best known, at that time there are no studies studying the sleep lengths in high temperature and pressure conditions, which are actual reservoir conditions. Therefore, in order to get better understanding on how the sleep length changes under high pressure and temperature conditions, we picked 4 temperatures and 4 pressures from low to high and permutated them. So here is the summary of our system. Again, the objective of this work is to study the sleep lengths under reservoir conditions. We chose 10, 20, 40, and 60 megapascal and 300, 350, 400, 450 Kelvin to reproduce the shale reservoir conditions. We used the 3-layered graphene and methane as the simplified model to reproduce the substrate and the fluid respectively. The length of substrate in the flow direction is 30 nanometer to avoid the final size effect. We adjusted the pore width as well to study the pore size effect. Our goal is to study the sleep length, and in order to achieve this goal, we went through several steps. First, we determined the number of methane for each system. After adding the specific number of methane in the substrate, we ran a short MVT to equilibrate the system. Then we add the external force to make the fluids to gas start to flow. And then we can calculate the sleep length based on the fluid flow behavior. I would like to introduce this step one by one. We use the in-house code and the software lamps using GCMC and GCMD to calculate the number of methane in the system based on the chemical potential. We have calibrated our result by comparing the average density from bulk region with density from the NIST chemistry webbook. We found that our result matches very good with the data from the NIST. Here is the density profile for the system under 350 Kelvin and 40 megapascal condition with different pore sizes. As we can see from the figure, the density converts to the bulk at the place far away from the wall. And near the wall, we can observe strong adsorption, and the first adsorption layer is not affected by the pore size. We studied the density distribution under 350 Kelvin and various pressure conditions as well. We found that the first adsorption layer increases with the increasing pressure, which came with no surprise. After getting the equilibration, we added the external force to the missing molecules. The relationship between the external force and the pressure gradient is calculated using the presented equations. Then we collected the average velocity change of fluids by time. And as we can see from the figure here, the average velocity came to the plateau after the 5 nanoseconds. Therefore, we use the trajectory after 5 nanoseconds for further study. We also analyzed the velocity profile for different pore sizes, and the velocity profile is shown like this. We use the following equation to fit and calculate the R squares. As we see from here, the R square is low for the relatively small pore sizes. Considering that the sleep is extremely sensitive to the NEMD velocity profiles and the NEMD results suffer from large statistical errors, we decide to use the mathematical method by using the flux as shown here to calculate the sleep length. We will not discuss in detail about these formulas due to the time limitation here. Finally, we get the slip lengths for the system with different pore size and pressure using the mathematical formulas which have shown in the previous slides. As we can see, for all pressure conditions, the slip lengths tend to vary to a constant value as the pore size increases. And the pore size effect is not significant for the high pressure condition cases, however, have a very significant effect for the low pressure condition cases. And here we get the question, why do this happen? As we discussed above, we use the flux to calculate the slip length, and in this case, the slip length is also related to the average density of fluid in the pores. Therefore, to exclude the average density effect, we calculated the reduced slip length by rescaling the slip length using the ratio of bulk and average density of the fluids in the pore. We found that the reduced slip length is less dependent on the pore size under low pressure conditions, which means the average density plays an important role in the slip length increment for the small pore sizes and the low pressure conditions. So here is the conclusion. The objective of this work is to study the effect of pressure and pore size on slip lengths under shale reservoir conditions. And in order to achieve this goal, we went through several steps, and we found that the first absorption layer is dependent on the pressure and independent on pore size. The velocity profile is parabolic for large width conditions. The pore size has a significant effect on slip lengths under low pressure conditions, and the average density plays an important role in such slip length increment. So this is the end of my presentation, and thank you for your kind attention. And here is the author list. So if you have any questions, please feel free to contact us, and we will be very happy to have further discussion.